Okay. So there we go. Okay. All right. So 16th. So homework 2. That's due tonight, right?
No.
23rd. On the 16th.
Can you get an extension on that?
I gave a lot of extensions for your database.
There's only so many of them.
I'm pretty reasonable usually, but this one's not that bad, right? I think some people, quite a few, hopefully have it done. I would love to see how many.
It's almost there.
I got that done last week.
I'll call you out. Who's got it done?
Okay.
I won't call you out by name, but at least just see what the number is. I've got 5, so just
So half the class is done.
yeah, half the class is done.
1, 2, 3, 4. No, mine is still not turned in.
No, I
No, I gotta add one more thing.
Oh, yeah.
said.
I was like,
All right.
definitely not turned in.
I have Is my sister's-
That's all right. Just go forward with it, submit it, I'll look at it, and then it doesn't have to be business. That's fine.
So I just put down.
Doesn't have to be business related.
I know just got put on the website.
Yeah, right.
Oh my Lord, you guys.
Yeah, that's enough.
I went,
It'll be off the web in 5 seconds. But maybe you get on there.
I went and spoke to a computer science class on main campus. It was like some class they do with seniors, and I was like guest speaker just to talk about my software company. And we went in, and the class like introduced themselves and like what they do. And a guy like completely deadpan says, "My name's blah blah blah. I maintain porn websites." And like, all right, and like,
There's money in it.
it wasn't true. It was actually he made it up, but he sold it so like perfectly. Because like later, I asked another student that I kind of knew. I was like, "Is that for real? Like that what he does?" And he's like, "No, he just made that up."
I say, I mean,
It's
there's
brilliant.
some big money.
Yeah,
some of it's amazing.
You have to stream, get to watch all these videos.
Oh,
all right.
Well, I know that you got video fine for it.
Yes, I don't need to be great for it. All right, so
Where's that?
back to appropriate topics, right? So that last chapter, we're going to talk about chapter 7 today, but in chapter 6 we talked about decision tables. And I didn't have a very good example in the slides. So there's some in the books, but I pulled out a couple more. So the idea with this decision table is we set conditions and then possible actions based on the decisions. This is a really simple one, kind of a banking thing. So the first condition is that what you're withdrawing is less than or equal to the balance in your account. And then you have to model. The idea here is generally you want to get all of the possible combinations of the conditions. So if you have 10 conditions, you end up with a pretty big grid here. Here, we just have, okay, this is true. This really doesn't matter then, right? If you have credit. If you don't have as much as in your account, so you're trying to withdraw 100, you only have 50 bucks. Then we have, well, you have credit, you have like an overdraft, or you can get a reserve line or whatever with running money. And then we have, you don't have enough money in your account and you don't have credit. So you have to have all the possible combinations here that make sense. And then the actions. In this case, you have enough money, you can withdraw. In this case, given these conditions, you can withdraw. So this is like super simple, almost too simple to be of use. You think you can figure that out without making a decision table. But here's an example of where it gets a little more complicated. So the idea is we're looking at a printer, and we have 3 conditions. The printer's not printing. There's a red light flashing on it, and the printer is unrecognized. This is kind of a made-up example. And then here's where our grid grows. So yes, 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 no, yes, no, yes. You have to have every possible combination up there. So we end up with 8. So it's these are binary. So it's like 2 to the third. So if you had a fourth or a fifth, it gets used, right? Potentially, depending on how. Sometimes there might be some of these cases that you don't need to model, but more than like 5 conditions gets pretty big. So 2 to the fourth would be 16, 2 to the fifth would be 32. So now these are binary, right? They're just yes or no. You can get into more complicated situations where they're weighted, and that's even more complicated. But the idea here is, given these rules, printer's not printing, the red light's on, and it's unrecognized, what action should you perform? Check the cable, ensure the software, check or replace the cable. So this lets you map, given any possible conditions, what you should do. So if it's unrecognized, but it's printer does not print, no, so it is printing. That doesn't really make sense to me, but there's no red light. Here you want to check the software. So you can map these inputs as the conditions and then create your action. So any of those troubleshooting things that you see online, like where it has you go through the steps, they're basically mapping to this. That's how they're, depending if you say yes or no, it's going to take you to the right part of this kind of table. So you can, in analyzing a business, you can build one of these tables. If you were trying to write software to help people fix their printer, you could map this out, show it to somebody that knows how the business works, and then use this as the rules for your software. So just summarizing chapter 6, we talked about those data flow diagrams. So showing processes, how the data flows through them. We had the sink and the source. So outside entities either pushing data into the system or taking outputs from the system. So we had some symbols. Processes were rectangles. Data stores are open-sided rectangles where the right side is open. We have the arrows for the flow. What were the sink and the source? Were they like just a different color? Oh, they were rounded on the corners. Yeah, they were rounded corners. Yeah. We talked about like decomposition. So you had the level 0. Well, first you had the context, which is the highest. Then you had level 0, and then you can keep breaking that down more specifically, and you end up with those like 0.1, 0.2. That's how far down are you breaking it down. Balancing. So the idea was, as you do the decomposition, the number of sink and source have to be the same. So you can't have at one level, there's one input and one output, and then the next there's 2 inputs. They have to stay consistent. So they have to stay balanced. We talked a little bit about using those for analyzing. We had that example of the IBM thing where they could save a 6-day process. Turned out 90 minutes of actual work was happening, but it was taking 6 days because of how it was passing around the organization. And they could cut that way down by restructuring the data flow. And that was what we called the business process re-engineering. So that was like, you throw the whole thing out and build a new, better way. So decision tables. And then the idea that you can model processes for internet-based softwares. Again, this is kind of a deep deal. So chapter 7, we're going to do 7 today, 8 Thursday, and then next week we'll do 9 and 10, and we'll be all the way through the book in 5 weeks. So a week after that, we'll schedule the midterm, the only real test of this class, and that'll give us a full 10 weeks to work on the project. So, what's that? better to have 10 than 6, right? So, I mean, I've been going quick through this stuff, but that's fine. I think we're getting out of it what we need to get out of it without spending way too, digging way too deep into some of this stuff. So chapter 7, we're going to talk about data modeling. For those you two and people on the YouTube that went through database, it's going to seem pretty familiar because it's the same kind of idea. And then for the rest of you, you'll learn something new today. We won't go as deep into it as we did in databases. We spent on ER diagramming. How long did we spend? Like weeks, right? We're going to spend like today. So once you get to databases, then you'll get to spend a whole lot more time. So some key data modeling terms we're going to talk about. Conceptual data model, which is what becomes this entity relationship diagram. So you use these for databases. They don't just have to be for databases. For modeling any kind of data storage, these are useful. We'll talk about entity types, instance, attributes, candidate keys, multi-value attributes, relationships, degree, cardinality, associative entity. So that's basically a bunch of stuff we talk about in databases, right? So how do we ask the right kind of questions to determine the data requirements for an information system? So the idea here is that we need to flush out, so we're in the analysis phase of the life cycle now. We need to really accurately flush out what the data that needs to be stored is at this point so that we don't move forward with implementation and not have what we need. So how do we get those? What are the right questions? Learn to draw entity relationship diagrams. Again, this is a rehash of some of the database stuff. Pull it. I don't really want. We're going to talk about all these, so let's just simple. So, conceptual data modeling. So this is basically a representation of organizational data. Now, it can also be the representation of data within a software system. Just depends on the scope we're talking about. So the idea is you want to show in this model what the data is, how are all the pieces related to each other, and any rules that affect that data. And ER diagrams are the most common way to use this. This is pretty ubiquitous throughout the software industry and then up into the systems analysis. So the whole idea is to model the data to create the accurate ER diagrams. As we learned in database, once we have a good ER diagram, there's a somewhat formulaic approach to taking that diagram and creating the database design out of it. There's a mapping process you go through and say, okay, the diagram has this is the table I need in my database, here's the setup. So, in order to do this conceptual part, it's really similar to requirements gathering, interviewing, questionnaires, joint application, design are used to collect that information. These are really dense slides, but yeah, not even talking very loud today. I'm kind of sick still. So it's animated. Yeah, don't get too close. So, of course, we have our data modeling. We also have our data flow diagrams, things. Everything needs to be consistent between those. So let's talk a little bit more about this in further detail. So when we're doing these conceptual data models, this book recommends the first thing we do is we model the current system. So this, of course, requires that there is a current current system, right? So if you're stepping in to rebuild and improve a system, start with the current one, build a model from that. That way you can see what's good about it, what's bad about it, and make it better. If you're starting from scratch, this step doesn't apply. The next step is that we build the new model to include all the requirements of the new system. So we have our old model, we've gathered all the requirements, that was chapter 6 that we talked about. We have to build a new model that supports all of those requirements. So if a requirement is that you need to be able to build this kind of report, that report needs data, so you better store that data, which means it needs to go into this data model. And then in the design phase, so we're in the systems analysis phase of the life cycle. Next will be system design. You'll take that data model and you translate it into a physical design. This is what we did in databases. Take your ER diagram, build your logical model that becomes your actual tables in your database. Right, after you normalize it and go through all that other stuff. So, yeah. So ideally, you have some repository that's linking all of this stuff together, right? So you're using some system to connect all these pieces. So, what are the deliverables from this? The primary deliverable is this ER diagram. Now, the book says there might be as many as 4 that you create through this process. The first would cover just the data needed in the project's application. There's the one diagramming what system are we replacing. ER diagram for the whole database from which the new application's data are extracted. So again, this is a data merging and transfer process. How are you going to get the data from the old system to the new? So you'll have a diagram from that. And then the last one, so I was talking myself into a circle here. Database from which the new applications data. Data for the application system. They're just separating the data from the application and the database. I mean, that's a kind of not really a strong line there to me. This one is saying that you're extracting data from the application. This is the system. I don't know, this slide. The point is that you're not just going to build one. You probably are going to have the big ones. You're going to have the new one, and you're going to have the old one. But you might have a couple for the old, depending on how complicated the system are. And you might have a couple for the new. So how are you transferring those? So this diagram here is a standard ER diagram. If you were in databases, hopefully this looks familiar and makes some amount of sense. So if I taught you anything through that class. So the idea here is we have an item. So this is an inventory type of system. It has a supplier to supply the item, and then it can be included on a shipment from the supplier. And then this item, yeah, so let's just look at this. So an item can have how many suppliers? 1 to many, and it's actually even more specified as 1 to 4, right? So an item can be supplied, the line here means 1. If this was a circle, it means it can be supplied by none, but that wouldn't make sense, right? It needs to be supplied by 1. This crow's foot means it can be up to many supplier, and then the reverse, a supplier can supply 0 items, but up to as many items as you want. Yeah, so we'll dig into this. I mean, for those of you that didn't take databases, we're going to break this down a little bit more. Right. Yeah, exactly. You're not getting the item from all 4 necessarily. Yeah. And then, you know, here's an item that's goes into a product. So it's like, this is one chip of the whole device, right? So an item can be in 1 to many products. A product has 1 to many items. Would make sense for it to have no items, because then what would it be, right? And then this is just a production plan. So we do have a couple of these that are optional mini. And then this one is the mini maximum. Now, why would you have an item and say it's only supplied by 4? Maybe you just, that's a business rule you have, is that you don't order items from more than 4 suppliers, and when you get to more than 4, you throw one out. You take the 4 best suppliers. I don't know, it seems kind of arbitrary, but
The contract is for suppliers.
right. So here's a, they say, oh yeah, this is just how it looks in Visio. I don't remember what I was doing here. It's the same basic thing, just showing if you made it in Visio, how it would look. So Visio is the, I don't know, the kind of long raining ER diagramming tool that Tom likes to use, right? Yeah, it's good. It's good. I posted a couple bullets on Moodle about ER diagramming tools. All I put was Lucid Chart and Visio because I really like Lucid Chart, and there's a free educational account you can get just by using your like EDU email. If you want to use cloud, I would just go with Lucid Chart. And if you want to use standalone software, I'd go with Visio. So I don't think, like, we're looking at 10 different project management softwares. There's a lot of diagramming softwares, but a lot of them are not very good. I don't think the pool is as strong as there is for yeah, and yeah, they're not as good. Yeah, or Visio. Yep. Or a couple people did use the tools in the MySQL, the management tools that they have inside them. So, all right. So the second deliverable is a set of entries about data objects to be stored in repository or project dictionary. So these are the data elements from our data flow diagrams that we talked about last time. If it's in the data flow diagram, it must be in the data model and vice versa. So if there's some piece of data, this is the connection between the two. Each data stored in a process model must relate to a business object represented in the data model. So it's again just the diversity. So how do we gather information for the data model? And again, we talked some about this in database. Really, there's 2 ways. Top down, which means data model is derived from an intimate understanding of the business. So if you know the business domain very well, you kind of just know the data that goes with it. Now, if you're hired as an analyst for something you know nothing about, like if I got hired for the banking, I know limited about banking, I wouldn't be able to do a top down. So bottom up basically is the reverse, looking at all the business documents to see what data they're currently storing, and then modeling a system to store it. Again, this is pretty ton of overlap with requirements, right? requirements, you did the same thing. You looked at all the documents and those kind of things. So just depending on the context, which of these is more appropriate. Hopefully it's a combination of both. It's nice if somebody has an understanding of the business that can be part of that process. Yeah, I don't think it probably does. And you get into this thing where you have engineers designing software for engineers, and they don't really understand the business process. So for our ER modeling, we basically have three chunks. We have entities, we have relationships, and we have attributes. So entities are kind of as the definition of an entity. They're a thing within our data. So that last slide had an item and a product. Those are things, they're tangible. Relationships are, we're just connecting the entities to say how are they related to each other. An item is related to a product. But in that diagram, a product wasn't related to a supplier, right? The supplier supplied items, not the product. We're building the products and shipping those. So you can see that in that diagram. There is no relationship between supplier and product. And then attributes. So each entity has some specific properties. Those are its attributes. Like an item would have probably an item number associated with it. It would probably have a cost. Of course, for us database experts, we know that that relationship would have a mapping table in between it, right? Because it was a one-to-many. And then that's where the cost would be, because the cost would be different for each supplier. So a detailed definition of an ER diagram, a detailed logical and graphical representation of the entities, associations, and data elements for an organization or business. So again, it's a business book. They're looking at this as like every data in a business, we can model in this. If you're thinking more of software, you can build an ER diagram for just what the software is going to store, which is what we'll do for the project. You'll do a ER diagram of some form for what data is in your system. Yeah, you'll probably do a UML and an ER and a data flow. And let's see, what other diagrams can I make you do? A flow chart of some kind. And I don't know. Yeah, by Monday, you know. So an entity, which we said is a person, place, object. It could be an event or a concept, but generally it's usually a thing. Is how I like to think of it. Something you want to store data about, an item, a product. In our scheduling software, when people are scheduled for, the people that are being scheduled, the employees. So in our ER diagram, they're rectangles. Entity type. So an entity type is a collection of entities that share common properties or characteristics. So we had the same kind of blurry definition in our database textbook. The idea is that an entity type is like an item. That's a classification. An entity instance is like one specific item. So this maps into when we get into the database. The rows are the instances. We have 100 items. We have 100 entity instances. We have one type. So, I mean, these are kind of the same thing, just depending how you look at it, the entity and the type. That's like the overriding classification, basically. But just differentiating that you're going to have multiple instances in most cases. If you were going to just store one item, you know, that's basically just like a constant, right? Like you need a table in your database to store that. Attributes, so these are the properties of an entity. I mean, there's a million of them. When you store an employee, you're going to store their first name, their last name, their phone number, their address. Hopefully not their social security number, so you don't have to worry about the security as much. All of the properties of that thing. Candidate keys and identifiers. So each entity type must have an attribute or set of attributes that distinguishes one instance from another. So candidate keys is any set of attributes that can uniquely identify an individual entity instance. So for an employee, and again, we're rehashing database class here a lot, you might be able to form a compound candidate key from the first name, the last name, and the phone number. That's usually pretty unique, unless you have like a junior-senior thing going on. What really ends up happening is you usually just generate a unique number, employee ID number, and you make that unique. Some things naturally have identifiers. Like if you are storing the social security number of a person, that's going to be unique in and of itself. Yeah, student ID number it would be unique in and of itself. So you wouldn't really need to generate a new unique number because you have a unique number. Right. So the idea is just if we have an entity with a bunch of instances, there has to be something to differentiate one from the other. Just to kind of boil it down as simply as we can. A candidate key is any of those things that would uniquely identify it. There can be multiple candidate keys. And then for those of you that were in database, what do we do for the primary key? Pick a candidate key, right? Like it's sort of arbitrary. Usually there's one that makes more sense. If you have a candidate key that's like, I have to take these 5 things and put them together and that uniquely identifies it, or you have a different attribute that's, well, they have a student ID number, you pick the student ID number. So here's just how these blocks kind of look. Entities are rectangles. Attributes, we just list inside. So we have the entity name, and then we have the pieces. We'll get into some of the other pieces on this diagram as we go forward. Entities are related together in either a unary, which means it's related to itself, which sounds really complicated, but you get into situations where you say an employee has a supervisor, so you have an employee entity, which is related to itself because one of the other employees is your supervisor. So that's a unary relationship. Yeah, it's recursive is what the database book called it, yep, because it's related to itself. Binary is just the simplest. 2 entities are related together, and then ternary is a 3-way relationship, and then there's n-ary, which is anything more than 3. The bottom shows cardinality, which we'll go into here in a little bit more, but the double slash means a mandatory 1. It means a 1 and only 1. So you kind of look at it from the outside in towards the entity. So 1 slash on the outer part, that's mandatory, that's 1. So 1 and then the second slash and only 1. Mandatory and many, so that's 1 to many. How is that optional 1? This should have a circle on it. There, the book has a pair here, so this should have a circle, which means it doesn't have to be in the relationship, but it could be in many relationships. And then, yeah, that's this one. So this one should be, this should just be X'd. Because there's only 3 possibilities here, right? 1 to 1, 1 to many, optional to many. This, that's right. You should have a circle and one slash. So there should be 4. Their diagram is totally whack. So it should be a circle with 1 slash. Optional to 1, basically. So breaking this down a little bit more. So identifier. So we have our candidate keys. We look at our attributes. We say this will uniquely identify it. The one we pick is the identifier. So we select it as the unique characteristic. In database terms, that's a primary key. If we're just talking about data modeling and we're not necessarily talking about database, we can just call that an identifier, which makes sense. It's what can uniquely identify something. So how do we pick the identifier? Choose a key that will not change its value. So student ID number, that never changes, right? That's a good one. If you pick, like I said, you might be able to do first name, last name, phone number. Does that change? Yeah, people change their phone numbers. So yeah, and you can change your name. So ideally, you'd use one that won't change. Now, here we're talking about looking at a business and picking this. As we saw in databases, usually we just pick the fake generated number. That's kind of separate from this, right? That's more specific to database. In modeling, they're kind of encouraging you select it from the data you're actually stored. But as we have seen, that doesn't always work out the best. Choose a candidate key that will never be null. So null means it has no value. Different than an empty string, or it's null. The phone number example, can a person not have a phone number? Yes, that's nullable if they have no phone number. Yeah, nullable. Yep, that's a real word. I'm not making it up. I know I make some stuff up. I make my own terms up sometimes, like mapping tables I made up, but nullable, Google it. What does it say?
It says, a made-up word by nullable type.
Yeah, there you go. It means it can be null, basically. It's nullable. So a phone number could be null. Avoid using intelligent keys. What's an intelligent key? To be honest, I have no idea what that is. It's in the book, and I put it in here, but I don't know. I've never heard intelligent key before. Probably need to get some smart key for.
We didn't know what a whiteboard scanner was either until we took this class.
Yeah, right. We've never seen that state-of-the-art 2007 technology. We were talking about last time. I don't know if you saw it, I think, but there's a diagram in the book, and it shows this giant scanner that would like scan a whiteboard. Like pan, it looks like it would slide across it, and like none of us have ever heard of that.
Well, actually, now,
That diagram was from the 80s, though, right? Isn't that what you decided?
Well, I was going to say, when I looked it up, I couldn't find anything on the scanner version, but they do make whiteboards now that they're like smart boards. When you write on them, they'll take a reverse image of what you wrote on them, and then you can make them stuff.
Crazy.
I guess that's the new scanner.
So number 4, I think intelligent keys means it's auto-incrementing or something. They're saying don't arbitrarily add one if you don't have to. Yeah, so it is what we thought. It means you're just saying add an arbitrary number that just increments as you insert data. Avoid using, though, how often did we use them in databases? Like on most of our tables, right? I mean, so it just depends. There's a lot of cases where that intelligent key, if that's what they want to call it, does make sense. But exactly. So that is one problem with the using intelligent keys, right? He's working on some data migration.
And this one has ID of 1, 1, 1, 1,
always have like, okay, all these have ones and all these have ones. And you get all that.
Problem is though, when you combine them together, you still have to have.
You still have 12 entries for one.
Yeah.
And then one, in this table has data.
And data migration.
Only one that has one. Yeah.
So the last one, consider substituting single value surrogate keys for large composite keys. So here's what they're saying is if you'd have to have 10 attributes to get something unique, then consider doing like the intelligent key, the surrogate key, to have one. If you have to have every single attribute as the key, what does that mean when we have relationships? That means you have to have all of that in the other table too. It means you're doubling your data storage, which is a disaster, right? So yeah, you'd have to, your linking tables would have to have that whole entry in them so that you could go back to the other table and find the right ones. Yeah. Multi-valued attribute. So an attribute that may take on more than one value. So remember, stepping back, say for example, a person, an employee has a phone number, you could have more than one phone number. Now, you diagram that into your ER diagram. When you build your logical diagram, that goes away, right? That becomes a mapping table, and then you have all the phone numbers. But in your ER, you have the multi-value. And there's a couple ways you could do this. A double-lined ellipse is one, and then our friends, the weak entities, which we had so much fun with before. So the double-lined ellipse is usually how I see them in ER diagrams. It's the straight line, and the dashed is the regular, which still makes no sense to me, but that's how it is. So the double-lined ellipse, this is kind of back to the old school way, like that I showed you in databases, not the crow's foot, but you just have your attribute, and then you had you had your entity, and all the attributes were listed in ellipses off of the entity. You just double circle it to say it could have two values. Now, in the crow's foot, you do the weak entity. It is way cleaner than the crow's foot. I don't know. The crow's foot existed, but that was not in our database book. And all the stuff I had ever learned, it was always the other way. So, but the crow's foot is better. Okay, so relationships. So we talked about entities, we talked about attributes. Now we're looking at relationships. So we're associating an instance of an entity type with the instance of another entity type, or if you have that recursive relationship. So association indicates that an event has occurred or that there is a natural link between entity types, like the item and the product. Items make up a product. An employee and the schedule of them for when they work. There's a natural relationship between those. They're always labeled with verb phrases. And this is where we get into the has a, is a, some of those that we talked about in databases. So we saw that on back, or I should have just exited the slideshow. Supplies is supplied by, sent by, this one's even better, supplied by goes into, composed of, and this would be like a has a product, has an item. Yeah, in this diagramming process. Yeah, you're trying to put it into an organized way that you can dissect it, but you're right. People will come up with things somewhat different. Yeah, I know that makes sense to me too. But so the idea, just kind of details and then step back for a second. We want to capture as much of the data as possible in the diagram, with the goal that we're going to be able to design a better system. So it's just kind of that's in diving into all this detail. Why are we doing this? And it makes a big difference. Like when I designed our orbital shift database, I did have to do some weird things down the road to make it work, but for the large part, I had a pretty good idea what data we were able to store, and that design and what I built off of the design worked for years and years without any real major problems with it. So the big thing is the maintenance. As you're experiencing with the data migration, the maintenance is a pain now because it wasn't very well designed the first time. So had they captured that initially and known, now here's the problem. They probably didn't know whenever that was designed that they were going to have all the data that was going to be stored. Things get added, and that's when it gets to be a gigantic. Because they don't know what they're doing. I mean, just to be blunt, that's just poor design. That part of it, and if they had done that all the way through, it'd be a lot easier. So that's one of the problems. Access just kind of does those things because it's access, right? It by default just does them because it's made for people that don't know what they're doing. That's sort of it's trying to give database power to somebody that doesn't know much about databases. So I'm always kind of harsh about access because I've seen countless things exactly like what you're going through, that something was built in access. Yeah. And you end up in these situations, and it's kind of one of those things. It enables someone that doesn't have the skills to do something they probably shouldn't be doing.
All the data.
Right. So, jumping out of our quick aside of our goal here, digging more into relationships. So, we're relating two entities, but really we're specifically relating individual instances. So, an individual item, this component, this chip, is related to an individual product, or more than one product. There you go. So degree is the number of entity types that participate in a relationship. This is where we get into the cardinality and the one-to-many. An item can be part of more than one product, unless it's some really specific case. So 3 cases. Unary, we kind of looked at these on the diagram. One instance to another. Binary, or one instance to itself. Binary, one to another. Ternary, it's 3. It's not the same as 3 binary relationships. So 3 binary relationships would be a relationship between this and this, this and this, this and this. My horrible triangle here. It's different than that 3-way relationship. The 3-way relationship means they're all simultaneously involved. And then there is anary. You can have more than 3. So here they're showing some example. A person is married to a person. That's unary. You're modeling one person, but an individual instance can be married to another instance. Yeah, that is still a person is married to a person, but then they're married to another person, right? Because in polygamous, it's not that the spouses are married to each other, right? Like if I had 3 wives, they're not married to each other. I'm married to each of them. Right? I think that's how it. but it's an individual instance of a person related to another instance of a person. Manages, this is the one I kind of did about supervisor. An employee is supervised by another employee. And then this has the crow's foot because this manages, whoever's the manager can manage more than one. Right, exactly. Binary relations, so this is just the kind of the simplest case. An employee is assigned a parking place. This is one-to-one. Only one employee can be assigned to a parking space, and an employee is only assigned to one parking space, unless you have two people are assigned to it, it's the first come, whoever gets it. But that sounds like a horrible idea. Oops. Product line contains many products. This is a one-to-many. One product contains many products, but a product only is part of one line. So you don't have
It's like a kit.
right?
You have many parts in that one kit, but still be only one.
Yeah, I always think of product line like makeup. I don't know, like they see the
Different
ad
colors.
campaigns, and this is this product, and then they have product line, and then they have all the individuals under it. If some lipstick is part of a product line, it's not part of another one. Student course. A student can be in many courses, and a course has many students. So this is not working. And then here we have a ternary relationship. Part, vendor, warehouse, unit cost. This is, see here, they're doing the dotted line, right? They're doing it as a week though, right? Don't you think? I think that's what they're getting at here. But did we ever look to see if the dotted line is a weak entity? Is that just our textbook or is that real? It just does not seem right to me. It doesn't. I don't think we ever like looked to see like. Do like crow's foot modeling weak entity. It makes so much more sense for it to be dotted. But all right, cardinality. So the number of instances of entity B that can be associated with each instance of entity A. So is this like super overwhelming to me? For those of you that weren't in databases? Okay. I mean, don't get freaked out. Like, this is database content. Like, we're not going to master this in one day, but just,
No, it's right.
yeah, that's why you have database class. And it just, it's supposed to be a prereq for this one, but because of scheduling, they kind of have thrown the prereq out of the window. So, yeah, which is crazy. So, I mean, we have multiple instances. Some people are real great at coding. Some people haven't had databases. We'll work through all this together. So
in the older model, apparently that
they changed it. Okay, so that the book's right then. So cardinality, and then we've been touching on this whole time. This one-to-many, many-to-many, one-to-one. How many times do you participate? In a standard person married to person, that's a one-to-one, right? One person is married to one person, unless we're modeling polygamy. We can also add in minimum cardinality. So remember, when we say one-to-one, one-to-many, we're talking about the maximum cardinality. With the crow's foot, though, and why the crow's foot is nice, we get minimum and maximum both. So minimum is the minimum number of instances you can participate. So do you have to be married? No, so that's a optional to one relationship. It has the open circle, which means I don't have to be married, and I can only be married one time legally by the laws of the state of Montana, right? So maximum cardinality, the maximum cardinality, but basically, if you're just talking about regular cardinality and maximum, those are the same thing. once you kind of include minimum, then you start calling the cardinality maximum, just because it makes sense then. So just kind of back to these. 1 to many, we don't have minimum on this diagram. We don't know, can a product line have no products? We just know it can have up to many, right? If we had a little line here, we know it has to have 1. It would make sense that it would, right? But 1 to many, we're not saying a product line has 1 to many products. We're saying one product line has many products. And that's where it's easy to get confused on how we read these. 1 to 1, that doesn't mean an employee is one and only one, even though that's what it would be. You're saying one employee to one parking space. Many students to many courses. Now, if we had minimum here, of course, we'd have probably a 1 here. We'd have a 1 here. We'd probably have a number next to that 1 to say like 10. Most courses don't run if they don't have at least 10 students in them. So, at least in our new academic or financial situation for the college. So, associative entity, so an entity type that associates the instance of one or more and contains attributes that are peculiar to the relationship. So if you have a relationship between 2 entities and you need to store data about that relationship, so for example, I kind of already touched on an item and supplier, there's probably a cost, right? You need the associative entity between those to store the unique cost of that relationship, depending on which supplier it is. And then these are really closely related to our mapping tables in our database. So here we have an employee and a course, and then we have this associative entity that's their certificate. What date did they complete the course? That's really the extra data we're storing. It'd be fine to say an employee is in many courses, all of that, but there'd be nowhere to store when they completed that course. So you'd have this middle extra entity data. So an employee can have 0 to many certificates. A certificate has 1 and only 1 employee. And then the certificate is only for 1 course. It says you passed this course and will have been issued optional to many times. If the course is started, the certificate never would have been issued. If a student's brand new, they never would have received the certificate. Well, like say I teach databases again in the fall, then there's 2 dates completed. And then also imagine it was like it could be a rolling online course or something and everyone can complete it at a different time. So our good friend, the Pine Valley Furniture Web Store, they do an example in here just to show again, and this is just the datedness of the book, trying to show that like, well, the internet's not that different than regular business, which I think we kind of already know, but they model this out with 4 entity types: customers, inventory, orders, and then a shopping cart. Why do we need to map the shopping cart as its own entity? Yeah, it hasn't been ordered yet. We want to store that so when they come back, their shopping cart is still there and ready to go, so they can buy that stuff. So we build this pretty simple diagram. A customer places orders. They can have 0 orders or many orders, but an order is only tied to 1 customer, 1 and only 1 customer. And then the order is contained in a shopping cart, and it contains 1 order. So, you know, it's related to the shopping cart because the state of the shopping cart at its last position is what's going to get ordered. That's where it'll feed the items that they're going to order. customer has a shopping cart, but they could have more than one, because you'd have one for every order that you've ever placed. What was the shopping cart when I ordered it? And then the shopping cart is connected to the inventory. So it has at least one item from the inventory. Your inventory might be in no shopping carts if it's never been ordered. Optional to many. Could be in many shopping carts, but it might be in none of them. So, I mean, that's basically the Pine Valley deal, just to show. I mean, we all did a web order databases, so we know that it's not a different idea. So the rest of this chapter goes into this idea of selecting the best alternative design strategy. I'm going to go through this stuff, but pretty quick, because it's really a business topic, but there's some interesting components in here. So 2 basic steps. First, we have to generate a list of what are the alternative strategies that we can use. And then 2, we need to select the one that's the best. But of course, we're not just randomly saying, well, I think this one's the best, let's do that. There's a process that we'll go through to do that. So the process, so we divide the requirements into different sets of capabilities. So you have all your requirements. You're going to gather a lot that are like basically wish list things that are fantasy that'll never happen. So you're going to take, and then some are basic and are going to be in every system, right? And that's just realistic. When you interview people, like I'm sure you could tell me 10 things that you wish your teller system could do that are like kind of like magic, but you still wish you could do it, right? Yeah. So you take all these requirements and you separate them out into 3 stacks. The middle case, the really high-end case where we get all these fantastical ideas, and then the kind of base version. Enumerate different potential implementation environments. So you're coming up with different ways you can get those capabilities. And then you propose the process to get those, whether developing software or obtaining software. And then the deliverables. So you need 3 substantially different strategies to build the system. Like I said, best case, worst case, middle of the road case. And then, what's going to be the most desirable. So to generate these, you do the low end. So this has the minimum functionality that users want. It's not necessarily a lot different than the current system. Maybe it's not different to their user point, but in the back end it ties in better, because that's the thing employees will always say is, well, why do we switch systems? This is like the same thing as the other one, but there may be good reasons that they just don't know about. Right. The high end, so this solves the problem that you're setting out to, plus has all the bells and whistles, the kind of best case. And then the mid-range, of course, is kind of a compromise between the 2 sides. So the book talks about drawing bounds. So how do you decide what fits into each of those buckets? Minimum requirements, you really got to boil down. Is it mandatory, or is this just something someone wants? It's the difference between, a need and a want, basically. Like regulatory things that it has to do to be compliant with banking issues. If you're doing a healthcare, the HIPAA stuff, if you're doing student, there's FERPA, those are baseline. You're not going to design a system that can't do those. Forms of features, so data outputs, analyses, user expectations. So just the book goes into these a little bit deeper. I mean, it's just basically boiling down what is really mandatory. Constraints. So, of course, we talked about like time is always a constraint, right? So that kind of limits low end, mid-range, high end, based on how much time do we have to implement this. Dollars. So that was that triangle I drew: time, dollars, money, features. There's a push between those. You can't make two sides bigger without causing an effect on the others. Elements of the current system that cannot change. So that puts a constraint on it if there's certain parts that has to remain. Legal, which is exactly what Amber touched on. Dynamics of the problem. So there could be a whole million other things affecting the constraints. So Hoosiers Burger, our good friend Hoosiers, they want to do a new inventory system. They want to replace their existing system, and then figure 715 in your book, and it's on the next slide, shows what the requirements are and what the constraints are. So system requirements, so you list them out. It's always good to put them in priority, because that helps you bucket them. Must be able to enter shipments into system as soon as they are received. That's the highest priority. System must automatically determine whether and when a new order should be replaced. Hopefully, most inventory systems have that, because that's kind of the point. Like when you hit 10, I don't know, burger buns, you probably should get some more buns. You know, but you shouldn't have to go manually check the system to find that out. And then management should be able to determine at any time approximately what inventory levels are for any given. I mean, these seem so basic. I would hope every inventory system has that, right? But and then some constraints. You can't cost more than $50,000 to develop the software, and you can't buy more than $50,000 of equipment. 6 months is the timeline, and you can't spend a ton of dollars and man hours training the new staff, So in descending order, so of course dollar things are pretty much always rise to the top. It's not an open budget. Ideally, the training is minimal, but if it's not, that's not as critical as dollars. So this next image will show the current system. So the current steps: they meet the delivery trucks, they unload, they log the invoices in them, accordion file. We're talking old school. They manually put them in a log. They print the report. They count the physical inventory, et cetera, et cetera. Just pay the bills at the end. It's completely manual. It's a mom and pop type of place. So 3 alternative systems that could be developed. So easy real-time entry of new shipment data. They all can do that. That was a high priority item that needs to be in all of them. Automatic reorder decisions. The worst case says for some items. So for the critical items in the system. The other B and C have all items. You have that. Real-time inventory, not at all available on step 1. And that seems pretty easy, but it is difficult, because what deducts the inventory? Unless it's tied to your point of sale system to say, I sold a burger and fries, connect to my inventory system and deduct a bun and a burger and whatever toppings I put on it, that's harder than it sounds. So that would take some more work. So that's why it's not on the low end. Some items, maybe it's realistic to do it for burger patties and buns, but not to track ketchup and when you need to order more ketchup, right? That's a little more complicated. And of course, the high end does it all. Costs, $25,000 for hardware and software, $50,000. So this is kind of right on the number. This is going $15,000 over to get all those bells and whistles. Time to operation, 3, 6, or 9 months. It's going to take longer. This is unless you're going to pump a ton more money into it, it's going to take more time. And then the training. So the basic system and the most complicated can be done in a week. because this one's simple, this one's hopefully good, really good. The middle one's going to take a little longer, is what they're estimating. Now, of course, I mean, this is pretty speculative, right? Like, this isn't rocket science. It's not like perfectly like laid out. So, how do you pick amongst those three? Like, in looking at it, I mean, my instinct would be like, well, go for C because it's not that much more and it's better. But of course, it's not that easy. So the book goes into this process, kind of like our decision tables, but where we do a weighting. And we try to do this not based on gut feeling and not based on instinct, based on a little bit more of a formulaic process. So the next figure will show how we do the weighted. So the left side of the table has the decision criteria. What are the constraints and the requirements? This is sort of like our decision table. We do the weights by discussing amongst the people that are going to use the system. How important is this? I think it's from 1 to 5. So each requirement and constraint. 1 is that it doesn't match the request well or that it violates the constraint. Up to 5. 5 is that it meets or exceeds it. So requirements on the left, constraints, and we weight those. So the alternative A, they all get 5 because we said they had that. Real-time data, this would be a 1 because we said it didn't have real-time data. This had real-time data for some. This had it for everything. So we apply these across, we score them, and then we have a weighting on the left of how important it is. These have a higher weight because they were more important. This has a lower weight. And then the same thing here. Cost is the most important. Training is the least. And basically, we just multiply it out and total up and put some numbers to it. So 425 is the score of the total for C. So according to the weights, C is the best choice. So the fact that the cost is higher, and we're rating that development costs, score 60 gets the lowest points here. Wait a second, does that make sense? Yeah. 250, I mean, this one you'd expect to be the highest because it does everything. It's 555. This one is higher because it costs more. How are they totaling up these numbers? 60, 120, these are just summed up. How does the rating play into that? 3 times 20, 4 times 15. Okay. So it's getting a lower score for development costs because it's more expensive. It's reverse of what you'd think that it costs more, but it's getting less points here. But it's getting more points on some of the other items. And then they're adding these together. How many requirements does it do here? And then it's going to have a higher score based on how cheap it is, how low is the cost. So this has a great score, A, because the cost is low, the hardware is low, all of these are low. So the total is the one that has the highest score, which the constraints, it's kind of reversed, right? Yeah. So that's kind of the end of that. Now again, I mean, it's good to do these kind of things in business school. They have you analyze everything with tools like this. Common sense and experience mean a lot. And these are good tools to help and also to help convince. This is why this is so easily manipulated. I could sit down and cook these numbers, and I could make any of these look the best. And I could go to ownership and say, we need to do A, look at this data I made, right? I mean, you can easily skew this. So, and that happens. We know statistics are easily manipulated, all sorts of things. So these can be useful tools. I just caution. If someone comes to you with this, take it with a grain of salt. Yeah, it gives you a starting point to put some quantities, because otherwise, really, it's just a shot in the dark. You're just saying, well, I think this seems like the best way to go. Well, why? Yeah. I learned a lot about that. All right. So,
The 2 years of MIS is enough for me.
signing off.